Hello students, in last lecture we have discussed the effect of temperature on reaction rate and Arrhenius equation and its derivation. Today we are going to discuss the next topic, that is energy of activation, interpretation of energy of activation and determination of energy of activation. Now, energy of activation is the minimum amount of energy of the reactant molecule must acquire before they could react. Only activated molecules are capable of reacting. In a given reaction, the fraction of total number of molecules that is activated increases rapidly with temperature and hence increases the rate of reaction. It is seen that the rate of reaction at a given temperature is decided by energy of activation. For each reaction, the existence of an activated complex characteristic of the reaction can be assumed. Now the figure shows that how the energy of reactant changes during the course of the reaction. Initially, only reactants are present. Its potential energy has a value ER. As the reaction proceeds, the molecules of reactants come into contact, distort and begin to discard or exchange atoms. So, the potential energy rises to maximum. Here, the reacting molecules have formed such a configuration that the further small distortion converts it into product. Such a high energy configuration is called as activated complex or transition state. An activated complex is not a stable species or reaction intermediate, but is one stage in the smooth and continuous transformation of reactants into products in the elementary reaction. The absorption of energy of activation EA by the molecules of the reactant converts them into activated complex, which is then converted into products. The amount of heat evolved during the reaction will be equal to the difference between energy of product minus energy of reactant. It is generally denoted as EP minus ER and it is equal to delta E. The concept of energy of activation is used in collision theory as well as theory of absolute reaction rates. Now we are going to discuss the next topic, that is determination of energy of activation. The energy of activation can be calculated by two methods. First one, graphical method. Now we know we already derived the equation, that is the Arrhenius differential form of Arrhenius equation, dln k upon dt is equal to EA upon RT square. This equation is the differential form of Arrhenius equation. So by rearranging this equation, we get dln k is equal to EA upon R into dt upon t square. Integrating this equation, we get integration of dln k is equal to integration of EA upon R into dt upon t square plus ln A, where ln A is constant of integration. Assuming EA to be independent of temperature, therefore the above equation can be written as integration of dln k is equal to EA upon R. It is kept outside the integration, and integration of dt upon t square plus ln A. Therefore, integration of dln k is ln k. Integration of 1 upon t square is minus 1 upon t. By substituting this value, we get the above equation as ln k is equal to EA upon R into bracket minus 1 upon t. It is the integration of 1 upon t square plus ln A. It is equation 17. Equation 17 can be written as ln k minus ln A is equal to minus EA upon RT. Therefore, ln of k upon A is equal to minus EA upon RT. By rearranging this equation again, k is equal to A into e raised to minus EA upon RT. From equation 17, we have ln k is equal to ln A minus EA upon RT. Now, by changing the base to the 10, we get 2.303 into log k is equal to 2.303 into log A minus EA upon RT. Therefore, by rearranging this equation again, log k is equal to log A plus into bracket minus EA upon 2.303 R bracket complete into 1 upon T. Now, if we plot the graph of log k versus 1 upon T, we will observe the straight line nature in the descending order. From the slope of the line, we can calculate the value of energy of activation. Now, in this case, the slope is equal to minus EA upon 2.303. Therefore, energy of activation EA is equal to slope into 2.303 into R. From the slope of the line, the energy of activation for the reaction can be calculated. It is the one of the simplest method to determine the energy of activation. It is called as the graphical method. Now, we want to discuss the next method, that is analytical method. Now, we know that just we have seen the equation log k is equal to log A minus EA upon 2.303 into 1 upon T. Now, let K1 and K2, these are the rate constants of the reaction at two different temperatures, T1 and T2. Then, the above equation can be written as log K2 is equal to log A minus EA upon 2.303 R into 1 upon T2. Similarly, for the K1, that is log K1 is equal to log A minus EA upon 2.303 R into 1 upon T1. These are the two equations. Numbers are 21 and 22. Subtracting equation 22 from equation 21, we get log of K2 minus log of K1 is equal to EA upon 2.303 R into bracket T2 minus T1 upon T1 T2. Therefore, the energy of activation EA is equal to 2.303 R into T1 T2 upon T2 minus T1 into log of K2 upon K1. In this case, R is the gas constant, T1 and T2 are the two temperatures in absolute, and K1 and K2 are the rate constant of the reactions. In this method, the rate constants K1 and K2 of the reaction at two different temperatures T1 and T2 are determined. Substituting this value in above equation, the energy of activation for the reaction is calculated. So these are the two very important methods by which we can calculate the energy of activation, that is by graphical method, and second one, that is analytical method. Now with this I will stop here and see you in the next lecture. Thank you.